So hope it is visible. So good afternoon. So we are in module 1 of wearable devices for medical applications. So the module 1 to 3 is mostly about embedded system designs, especially module 1. It is about system design techniques. So we are seeing the fundamentals of embedded system designs. So in the last class means we have seen till optimizing the design metrics. In the last online class, I think we have covered till classification. No, it is overview of microprocessor and controllers, and we have just seen till embedded hardware units and devices in the system. So today we'll brief the design process, design metrics, and I think last class we saw design challenges, optimizing the techniques in designs, and then we'll finally see the skills required. So with that, skills required for an embedded engineer is a small title. So with that, this module will get over, and after the Pongal holidays, we'll start module 2. So moving on, we'll directly go into the design process slide. So even last class we saw there are 8 design steps that are involved in embedded system design. So first one is quickly to go through. It is abstraction, means getting the design requirements from the customer or the consumer, whosoever it is, and then based upon the requirements, we need to decide which hardware to use, processor or microcontroller. If it is microprocessor, which microprocessor, or microcontroller, which microcontroller. All these things, because it depends upon means there are so many design constraints as far as embedded system is concerned. Like last class we saw the limiting factors, right? So based upon that we'll decide it, and then we have also to finalize. There will be a main agenda to be targeted in embedded system design. Apart from that, there can be extra functional features or upgrades which also has to be considered. So that has to be finalized. Then we need to check whether people have worked in the similar area, right? Similar designs are available. If so, we can slightly modify or fine tune that, something like that. And whenever we start, and then it's about starting the system design. So while starting the system design, whatever we do should be in modular structure. Modular structure means in the form of modules, right? So a separate modules has to be designed so that these modules can be reused in the future designs wherever it is required. Then it is about mapping the data as well as the program flow so that we can understand where to fine tune or optimize it later, because there is program optimization, there is memory optimization, as we've seen last class. And then then the 7th step is about user interface design, and finally it's about optimization. Similarly, the second title that we have seen was design matrices. So design metrics are measurable parameters that are used to evaluate or appraise the embedded system that has been carried out. So that depends upon the first parameter is NRE, non-recurring cost. So this is the amount spent for the research and development. And then unit cost. So this is the actual cost that is taken by the embedded system, a single unit. And then it is about the size. So size doesn't means only about the physical size of the unit, but also it means about the memory size, etc. Then about performance. So we need to also evaluate the execution time, the memory fetch, and all these things. Then the 5th matrix is power consumption, flexibility, time to prototype. So flexibility is also important feature, whether the system design is flexible for future upgrades or modifications based upon the comments or the troubles faced after launching the product. So all these comes under flexibility. Then time to prototype, time to market. So these are very important parameters which effectively plays a role in the success of an embedded design. Then about maintainability. So how far we're able to modify a system after it's being launched, right? So then the correctness is about how far we have achieved the target or the design requirements. So that's about correctness. So correctness is a parameter. So where will indicate that this design that we have designed matches this many percentage. So it's not just we give some value. So based upon some analysis, we'll tend to justify that percentage. Then we saw, as last class, we saw some design challenges. So the first design challenge is stability. The embedded system design should work stable in all the environment. The behavior should be stable. If it is going to change, then it's a question. So stability is always an important parameter, because uh, we're really not sure in which environment an embedded systems could be used. Or if there are some limitations, that has to be said as a note that this equipment can be used only at indoor purposes or at outdoor purposes only, something like that. So the second one is security. Since all the embedded systems are nowadays becoming smarter, and everything is almost IoT enabled, since it has to be accessed from everywhere. So the network uh, hacking issues or security breaches is an important parameter to be always considered, or it is always a challenge. And the third challenge is launch phase, time to market, and time to prototype, time to revenue. So it's all an important challenges or issue regarding the embedded system design. And always, as we have seen right from the characteristics, an embedded system will have so much of limitation or parameters that has to be considered. So few influencing limitation factors are the processing power, the battery life, how compact the design is, and then the cost of the, finally it's all about money, right? So it's cost of the product. So only then everything falls on in its place. So then the fifth design challenge is integrity and compatibility. So integrity means it is not about the parameters or anything else. It is the integrity between, or cooperation between, the software engineers and the embedded system design engineers. So embedded system design engineers work with lots of constraints, design constraints, whereas the software engineers has to be well explained about uh, what all things has to be done, how the embedded system functions, communicates, and all these things. Else, they'll blindly take some ready-made codes, modify, alter, and then they'll give it to us. So that's the style they work on. So that's always an integrity is always a challenge or a problem or an issue. Similarly, compatibility. So our embedded systems should be compatible in all environments. Then we saw about optimizing the design matrices. So there are four types of optimization techniques. So one is code optimization. The second one is memory optimization. Third one is power optimization. And finally, performance optimization. One has to understand that optimizing one of these parameters might conflict with the other. Means, for example, when I tend to reduce or squeeze the code, it might result in some other compromise. Either the performance will fall down, or for example, if I tend to increase the performance, either memory utilizations might be more, or more power consumptions would be there. So always there is a compromise, or there is always a conflict between these optimization techniques, which one has to sync with all the four optimization techniques and finally come up with a solution or agree to whatever method they take. So code optimization is about reducing the length of the program. So when we reduce it, the more faster the code will run, something like that. The potential memory, the program memory use will be less, the CPU load will be less. So this is one of the technique which will improve the efficiency. Similarly, memory optimization. So memory optimization means how do we utilize RAM, ROM, and all these things. So how do the data flows in and out? How do we process the data? And all these things comes under memory optimization. Similarly, power optimization. So it's about how do we do the power management, background apps, and all these things will come under power optimizations. Then performance optimization is about modifying or fine tuning the functioning of the system. So for example, this always aims in increasing the speed, efficiency. So efficiency means uh, how well we produce an output for the consumed input. For example, what is the input power that we consume and what is the work that has been done. So that is what actually efficiency is all about. So how do we optimize this? There are so many techniques to go more in detail of increasing the speed and efficiency, any of them. So that results in performance optimization. So this is what we have seen so far, right? So today we'll see about the skills required for becoming an embedded system designer or embedded system engineer. So basically, to develop an embedded system, these are the skills that are being required. So we would think, why should means it's for embedded system design engineer? No, how do they correlate with our subject? Is wearable devices. So these are, for example, there are wearable sensors. So these will be finally, or it will be interfaced to some embedded systems, and from there it is going to communicate to our internet, either through wired or a wireless manner, into the monitoring system or the control unit, which is at the remote place. So the knowledge of embedded system is very much required, or the skills to design an embedded system is very much required. That's why this subject carries almost 3 units about embedded system design. Right now, these are some skills which are required to become a good embedded system design engineer. So one is C or C++ programming. So the knowledge of these C++ is very fundamental and very necessary nowadays, because any high level language you take, it all depends upon, the foundation depends upon C++. Even so, how does the C programming helps in embedded? For these processors, right, we have something called as embedded C. So it is an integration, or it is a C program that is exclusively developed or altered to address or to facilitate the functioning of, or the programming of, an embedded system. So in the beginning, so the programming was in assembly level language. Any of the microprocessors you would have studied, so it's a prerequisite in from the bachelor's degree. So when you have studied microprocessor, microcontrollers, we would have seen that the microprocessor, the code is written in assembly, and any of the microprocessor will understand the program only in binary. So writing a program in binary is not possible. So we'll tend to have an assembly level language program. Like we'll take the assembly program sheet, enter an equivalent hexadecimal code. That's how we tend to program. So that is a tedious task. So as the processes evolved, the programming methods also evolved. So from assembly level language, they went on for higher level languages like C. So the C, that's what, it's a stripped down or a modified version of C is what embedded C. So what is the difference between embedded C and C when you ask? It is like, if see, if it is like, if I call some program as or something as embedded C, it will have unique commands which can be used to program or to address the timers, counters, and all these things. For example, there can be so many registers inside, so that can be set or reset by just in one single code from a C program. So this is an exclusive, embedded C is an exclusive programming language for programming the embedded systems or microprocessors and microcontrollers. So a fundamental knowledge in C++ would help us in writing the code in embedded C programming, correct? Because fundamentally it's all about the logics. Logics, as you know, in C, if, else, while, and all these things will come under it. So the very basic programming skill that is required to become an embedded system design engineer is C, C++, C or C++ programming knowledge. The second one is some knowledge about, so this is very mandatory, and this is to at least to a certain extent we should learn to work on the algorithms, optimization algorithms, or algorithm optimization skills, or another way, optimization algorithms. So as we have seen in the last title, there are different types of optimization techniques in different levels. So first level was we saw it is in code optimization. So how does code can be optimized? So when I taught, you would have thought like we take the main program, we reduce the code, we make some loops, uh, and we call it whenever required. That's all okay. If it is a small application is concerned, how about when the code goes more than 1,000 or 2,000, 10,000 lines? How to do it? So that's where these optimization algorithms comes into picture. So these are probably in today's era, or and the updated thing is there would be some optimization algorithms which are AI powered, where when you feed it your program, it will tend to make a better, shorter, faster executable codes. So that's always possible. So a little bit knowledge, at least, about these optimization algorithms is much more necessary. And the third skill that is required is reading, ability to read the schematics and pinouts. For example, we tend to work on. Imagine the situation like this: we are joining a company, somebody has already left, and he has made some design, and this is the sketch or circuit diagram of somebody's design who has already done, and now we have a problem, now we need to upgrade. So when we check the previous design, this is available. So now so probably he would have worked in some uh, softwares like Altium or something else. You would have knowledge in some other software. But fundamentally, an embedded system design engineer should have a knowledge to read schematic diagrams. So we should have the knowledge to, at least, or we should develop the knowledge to read out what are all the pins by seeing the data sheets, how it is being connected, what is there in between, and how much power it does uses. And some all these things are fundamental to this is again a fundamental skill. So this is recommended skill, the second one, and the first one is very mandatory. Similarly, this is also a very mandatory one, to read, to interpret the data from the schematic. Schematic means the circuit diagram. So that is more important. So there is a meaning for the red line, blue line, green line, and all these things. So we need to interpret the data. Only then we can carefully review, and then we can make changes or use it, upgrade, do whatever is required. Right. So this skill is very much important. So that, for example, if you want to become an embedded system design engineer, or we have decided to work in embedded system design, then that is one more important skills that has to be developed. Then this is also one of the mandatory skill that is necessary. So that is knowledge, or knowledge about digital interfaces. As I have said earlier, this beginning of this class, we will tend to interface these wearable sensors along with some microprocessor unit. For example, if you are going to monitor a patient and the patient is at home, we have given them the permission to move home, and we have put some wearable flexible, means it's not a rigid sensor, some wearable sensors then and there, like you put a gloves and you place a wearable sensor there, so that you want to monitor something. So now all these sensors would be connected to some microprocessor or a controller, and from there would be a model like a transceiver connected there. From there the information is going to flow. So the knowledge about the interfaces is much more required. For example, the interfaces can happen at any kind of ports. The interfacing can be in can be a serial peripheral interface, or it can be I2C interface, that is integrated circuit interface. It can be an UART or USART, right? So it can be general purpose IOs method, whatever it is. So these knowledges are much more required. So we have to develop that also, these skills also. So, and the fifth skill that is required is, see, this skill, this fifth skill, like second, this is an optional one. If we learn to work in this, it will be better. Like basic Linux installation and commands, the knowledge in basic Linux installation and commands is recommended. So certain skills are mandatory, certain skills are recommended. So little bit knowledge about the Linux installations and all this is very much required, because Linux is an open source platform. So everybody works in it, and everybody modifies this raw version of Linux and makes their own version. And the knowledge about the Linux distribution and the knowledge about working in the Linux platform is much more required. Though we always use Windows platform, we Indians, our people in United States, we use Windows platform, but the people like in China and this Japan, so they all use the Linux platform more because it is open source. You have the freedom to modify the operating system itself, and you can make your own Linux distribution. So this knowledge is recommended, and some of the Linux commands is more required. And the sixth skill that is required for an embedded system design engineer is flashing, knowledge in working in flashing tools or debugging tools. So what is this flashing tool you would have come across, like flashing the cell phone, something like that? So when the embedded system doesn't work, or you need to reprogram the embedded systems, finally there'll be, as I told, there can be EEPROM, something, or you want to replace your program. That's how it is. So we need to know how to flash the read-only memory in the embedded system. For example, that's actually what they do in cell phone. In the ROM, there would be an operating system running, some version of the Android, and you can flash that ROM and you can forcefully upgrade your ROM if you have the knowledge of flashing and debugging tools. For example, I've tried. So in Android, when you go to about phone, when you press the release version, I think for 7 times, it will tend to enable the developer tools. So after enabling the developer tools, you can go into, there are many flashing programs available. You can go and means they select the right model of the cell phone. So it will tend to connect to the phone. So connecting through the phone, again, it can be through Bluetooth or it can be through an USB bus. So once it is connected, then you, as a developer, you'll have an access to flash the operating system itself. But it's a risky one. So normally you will not have that access or that options. So that is only for developers. So we need to, as an embedded system design engineers, when we want to use the resource which is already available and flash the program alone, or you want to debug some code which has crashed due to some misuse. So then you need to have some knowledge at least, in working with this flashing and debugging tools. So that is one of the qualities or skills that is required for an embedded engineer. So these are the 6 skills that is required. Even there is one more point. So probably it comes under Linux platform itself. That is the knowledge of working in. So that is an optional skill. I think I've missed to mention it. So knowledge of working in Python. So nowadays, whenever you want to work with artificial intelligence, machine learning algorithms, or something related to image processing, video or image, something like that, Python serves better than the MATLAB. MATLAB is also good, but MATLAB is a licensed software, where Python is again an open source. So some knowledge of Python is also becoming an additional skill that is required for an embedded system. So these are the skills that are required for an embedded system design engineer. C, programming skill to work on embedded C. Some knowledge at least to work on the optimization algorithms or the programming tools, and then a mandatory skill of reading the schematics, understanding how the design it is, reading the pinouts, means what voltage will come. For example, when we open an embedded system, pin readouts has to be done. For example, we are troubleshooting it. So this port, this point, we're at this checkpoint, what will be the voltage? All these things we should know how to do it. And then working on digital interfaces a little bit. This is an optional. So working in Linux and Python. And then this is a mandatory one. Like we need to know about some knowledge in flashing and debugging tools. So these are the skills that is required for an embedded system design engineer. So with this, this model gets over. So I think we have completed the module, and the two online classes, I think I have covered the entire syllabuses. So if you missed the classes somewhere, though not detailedly we have discussed, we have just refreshed it. So you can see the videos and you can understand. If there's still any doubt, you can just contact me. Okay. So thanks for joining. See you all after Pongal. Bye-bye. Take care.
Thank you, sir.